Hello, this lecture will cover pages 116 through 117 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Additional Analysis Techniques, Chapter 5D, Working Chapter 5 Problems. Before we do pages 16 and 17 in our lecture notes, I want to start out just by working some problems in the back of the book here. I want to start out with problem 5.8. This is what it looks like here, so you don't have to turn in your book. It's basically this problem here. And notice it's a 2K ohm resistor in parallel with a 6 milliamp current source. There's a 1K resistor, 2K resistor, another 2K resistor here in series with a 12 volt source. No dependent sources. So don't have to worry about any other considerations other than just trying to find the value of V out, which is essentially the voltage across this resistor, which is that point right there. If this is a ground reference, V out is right there. They want you to find V out. Now the answer to that problem, if you take a look, is 7.5 volts. What I would like you to do is, I'm going to give you some hints here on some things, and then I want you to take a piece of scrap paper, and I want you to work this problem out by superposition. I want you to work it out by nodal analysis. I want you to work it out by loop analysis, and I want you to work it out using Thevenin's theorem. You're going to use 4 separate tools from your toolbox. And this is a nice problem to work these tools out with. And if you can get 7.5 volts, and you should, in all 4 analyses, then you're starting to get a handle on working these problems. Perfection just comes with practice. And you have to set aside some time to work problems. You just have to. They're going to look easy when I do them. They are. But you have to hit that wall on your own and then break through it. And then this won't be so... It won't be difficult for you. So let's first take a look at how you'd work this problem by superposition. Well, basically, you have to find the voltage at this point with respect to here. And you have 2 sources. So you first find V out prime by reducing this to 0. How do you do it? You short it. And you use this simple 6 milliamp source to find the voltage at that point. Then you're going to have to find the equivalent resistance over here, which is 2K in parallel with 2K. That's 1K plus 1K. So you have 2K ohms from here over. 2K ohms. You have 2K ohms over here. So that current's going to split to 6 milliamps. That 6 milliamps is going to split to 3 milliamps in this direction and 3 milliamps in this direction. Okay? And then it's going to split again at this point between here and here because that's a short. Once you work that out, and you get this current, you can find that voltage, but that's only half the problem. Then you have to go back and find out what this voltage is with this in the circuit, with this being reduced to 0, which is open. Simple analysis. And you find V out by adding up algebraically V out prime and V out double prime. And you should get 7.5 volts. Nodal analysis. How are we going to work this out with nodal analysis? Well, this is what I suggest. I would make a node here and I would make a node here. I'd call this V1 and I'd call this V0. Don't put a dummy variable of V2 and it's already labeled as V0. Remember that? And then what I would do, and you're allowed to do this on a test, you could work this out with nodal analysis and sine currents, and the current here going in this direction is V out minus 12 divided by 2K. But why not do this? I suggest doing this. I'm going to replace everything to the right of my pencil. That's just a voltage source. I can find a short circuit current from this point here to this point here. Basically convert this to a current source like I have down here. So take a look here. Do you understand that this circuit is the same thing? The circuit to the left of my pencil sees this and this is the same thing. One's a voltage source, the other one's a current source. I'm just bringing the 2K down in parallel, and I'm finding the short circuit current between here and here, which is 12 volts divided by 2K, which is 6 milliamps. So what I can do is replace this with a current source. Maybe it's easier now to do your nodal analysis because you have one node here and you have another node there. You work it out, you find V0, you divide by your 2K right here, and you should get 7.5 volts. What about loop analysis? Well, you could go ahead and do loops over here, do one loop. Remember, assign this current here. Just don't go through here again. I mean, this is a source. So if you assign this as I1, you can't have I2 going here. Remember that from that chapter, I guess it was 3? If you assign this as current I1, this has to be I2, and this has to be I3. So I1 would be a minus 6 milliamps. But forget about that. Why don't you just take this? Everything to the left of my pencil is just a current source, a Norton equivalent, if you will. I'm just going to find the short circuit current between here and here. Okay, I'm sorry, I'm going to find the open circuit voltage between this point and this point. Or if you prefer, here to here. It's the same voltage if this is a reference. I'm just going to convert this to a voltage source, and I do. 6 milliamps times 2k ohms is 12 volts, and I bring the 2 ohms up. If you don't see that, just put the 6 milliamps over here and put the 2k over here. They're in parallel. Everything to the left of my pencil looks like everything to the left of the pencil down there. Let's do this. There. This circuit over here sees both these circuits as the same thing. Now, do your loop analysis. Find the current I1, find the current I2, find out if the 8 are opposed one another. Take that current through here times the 2K to get V out. You should get 7.5 volts. And then finally, for Thevenin's theorem, you want to find V out using Thevenin's theorem. You remove the 2K resistor. Remove that 2K resistor. If you have to redraw the circuit, redraw the circuit. If you can't picture this not being here. And you want to find that open circuit voltage between here and here. But before you do it, you want to find R Thevenin. You reduce all the sources to 0 because there's no dependent sources. So you can open that one and short that one. And you look back in there and you should be able to see what R Thevenin is equal to. And then find the open circuit voltage with that resistor removed between here and here. Once you do that, and it's okay to, in that problem, use this as a tool. You're working Thevenin's theorem, but you might need this or this or this as a tool to find that open circuit voltage right there with that 2K resistor removed. Once you find that, you find the Thevenin equivalent circuit. You find E Thevenin. You already know R Thevenin. Don't forget to put the 2K back on. Students forget that. You put the 2K back on, and you find what V out is. 7.5 volts. I definitely turn off the video now. Spend yourself 20 minutes until you get it, and work 5/8 out 1, 2, 3, 4 different ways. You should get the same answer. And that answer's 7.5. 7.5 volts V out. The next problem I want to look at is one of the homework problems. It's 525. This is problem 525. No dependent sources. I want you to find V out by Thevenin's theorem. And I'm going to add one more thing. I want you to find the maximum amount of power that can be delivered to that 2K ohm resistor. Because that's what they're saying V out is across that. So the first thing you have to do is remove this and label the terminals A and B. So you're removing this part of the circuit because they want V out. That's the load resistor then. You remove the 2K. So you first remove RL from the circuit, and then everything's by inspection here. Don't even need a calculator here for this part of it. What's R Thevenin? Looking back into the circuit, what's R Thevenin with these reduced to 0? Well, don't forget the 2K isn't there. This is shorted and that's shorted. What's simply 2K in parallel with 4K. That's 1.33 k ohms. You're halfway done with the problem. You have the R-Thevenin resistance is 1.33 k ohms. Just don't break any rules here. What's the open circuit voltage? With this removed, what's the voltage between this point and this point? What's that open circuit voltage? Between terminals A and B, if you will, when you label terminal A and terminal B. Well, by inspection, I can see what it is. This contributes no current to this part of the circuit because it's open over here. It just supplies voltage. So what part of this voltage is across this resistor, with this being a reference point? Well, it's a -6 times 4K divided by 6K. It's the voltage divider rule. Now, you're used to seeing the voltage divider rule real nicely written like this, or shown like this. Have a nice little voltage here, which is 12 volts. We'll say you come over like this, you come down like this, you come down like this, something like that. And they want to know what the voltage is between there and there. It's the total voltage times this resistance divided by the sum of the two. But this can be anywhere in the circuit. These resistors can be anywhere in that circuit, just like they are here. I want to know what the voltage across this resistor is, 4K resistor. It's a -6. If I'm using this as a reference down here, that looks like a minus voltage with respect to this. This is more positive. So it's a -6 times the 4K divided by the 6K. That's the voltage at that point with respect to this. Remember that we want this open circuit voltage down here, minus the plus. This is out of the circuit. You're working a Thevenin equivalent. And then you just, if you know that voltage there, which is this, you just add 12 volts to it, minus the plus. So if that turns out to be a -4 volts, plus 12, plus 8 volts. So you can go straight to the Thevenin equivalent. E Thevenin is 8 volts. I draw it very neatly. R Thevenin is 1.33 k ohms. Put the 2 k ohm resistor back on. What's V out going to be now? Well, V out's a voltage divider rule, like it is in most of these problems with Thevenin. It's the 8 times the 2K divided by 3.33K. It's 4.8 volts. That's the answer to this problem. And then I wanted to know what the maximum amount of power to this would be. Well, we know the equation for that. The equation for that is E Thevenin squared divided by 4R Thevenin. I'm just using that value and that value in this equation. I get 12.03 milliwatts. That's problem 525. If you take a look, I guess we could go back and take a look now at problem 519 I have posted. In 5.120 I have posted. These problems here are homework problems. And I have them posted and labeled everything clearly. Notice in both 5.119 and 5.120 we have dependent sources. We have dependent sources in both of them. So in order to calculate R Thevenin, so we can use this equation, I had to find E Thevenin and I had to find I Norton. I had to find the open circuit voltage and the short circuit current. Now, I redrew the circuits, but to save space here, I didn't show the redrawn circuit, but I'm sure you can redraw the circuits to get these equations here. This one, I just opened it up, and there's the equation. Down here, I just basically shorted from here to here, and there's the equations. And then in problem 5.120, same thing in problem 5.120. Notice it has a dependent source. So, if it's asking you to find anything to do with power or Thevenin resistance, you're going to find somewhere E Thevenin divided by R Norton. So it makes two problems on it. Notice I'm finding E Thevenin up here, and I'm finding I Norton down here. Notice you can't have negative resistance. So if this turns out to be a negative value, this better turn out to be a negative value. So you have a negative over a negative. You end up with 2 ohms. So for maximum power transfer for that load resistor up here, this RL up here, has to be equal to the Thevenin resistance looking back in, and I calculated that to be 2 ohms through these equations. These equations are nothing more than Chapter 3 equations. You've done each of these in Chapter 3. It just makes 2 problems out of it. And then finally, we can get to page 116 and 117, which is one of your homework problems as well. It's problem 5.118. I guess we're going backwards in our homework problems, and I will go over this one in detail to finalize this lecture. For the circuit shown below, determine the value of RL for maximum power transfer to RL, then determine that value of power. Here's the circuit. Just don't break any rules. Reach into that toolbox and pull out some tools. You just don't break any rules. And I'll show you what I mean by that. We're removing that load resistor. That's what I did. With that load resistor removed, label the terminals. What I want to do is I want to find that open circuit voltage between A and B. That's going to be my Thevenin voltage between there and there. Now, I just can't tear into this circuit and try to find the value of RL for maximum power transfer and say it's R Thevenin, and you go right in and just open that and short that. Because that's a dependent source. We have to find E Thevenin. And down here, if you look at that circuit, can you see, this is what I mean by just being confident with your tools. And this circuit right here, that's open circuit. By Kirchhoff's current law at node 1, I's coming in, that's given in the original problem, that's a plus I, plus 100I, it's coming in, that has to equal 0. There's no current over here. So the sum of the currents entering or leaving that junction algebraically has to be equal to 0. That is a plus I plus 100I equals 0. Solve that for I. I is equal to 0 amps. You didn't break any rules. If this current I is equal to 0 amps, if this is a reference right here, which it is because that's point B, we want to find out what VAB is, open circuit voltage. A with respect to B. B's ground. You're up 12 volts here, and there's no current flow because I equals 0. There can't be a voltage drop there. So V open circuit has to be 12 volts. There it is. There's your Thevenin voltage. Turn the page. We're trying to find our Thevenin, and we got the numerator now. We got the 12 volts in the previous problem. Now we have to find I Norton, so we can find that 99 ohms. Why? Because of that doggone dependent source right there. So, but look how easy it is. The same circuit, except you short this out now. It's the same circuit. Instead of finding the open circuit voltage, you find the short circuit current. You just draw that from here to here, and you find that current. The current that's going to flow from here to here to there. Well, that's node 1 still. At Kirchhoff's current law, at node 1, we know it's I coming in, plus I, plus 100I coming in, minus this short circuit current, which is the Norton current. It's the same equation we had, except we're adding this term because that's no longer an open circuit. I short circuit is 101I. Well, we know what I is by looking at that. If that's a short between there and there, this is ground reference, that's ground reference. This current I is going to flow here. That's I. So you take 12 volts divided by 10K. You couldn't do that if there was a resistor down here. But there's no resistor down here. That 12 volts is entirely across that 10K. That's 1.2 milliamps. That's I. Now you know I. Now you can find out the short circuit current. It's 121.2 milliamps. That's your Norton current. We know that R Thevenin is equal to E Thevenin divided by I Norton. There's your Thevenin voltage we found on the previous page. There's your short circuit Norton current. We found it on this page. You get 99 ohms. So in this problem right here, now we know E Thevenin and we know R Thevenin. What's the value of RL for maximum power transfer? 99 ohms. What's that value of maximum power? E Thevenin squared divided by 4R Thevenin. We used this many times. 363.6 milliwatts. All the problems work out like this if you just do it systematically and take your time and build up some confidence. Most of the problems at the end of chapter 5 here I have posted. So I want you to take your time and look through them, try to work them out. If you have any questions, contact me for office hours. That concludes this lecture.